Okay, welcome friends. This is the 10th session of ARM-based development course. I hope so far you have been able to follow. Very happy to share this information with you guys. Now, today we will be going deeper into the addressing mode 2 and then 3. So, in the last session, we saw how internally the ARM data path functions when this addressing mode is used. So, in this discussion we will see what all the different ways we can provide the offset address which is to be added with the base to access the memory. Okay. So, this session will cover addressing mode 2, explaining all the formats that are supported. I will be giving you sample programs and then what is the condition before the executing that instruction and what is the status after that instruction is executed. And all instructions, whenever we use R15, we need to be careful and we have to be aware what is the difference when we use R15 in an instruction. So I will cover that part of that here, as well as what is the instruction time for executing on load LDR or SDR. How much time does it take? What are the different cycles used by that instruction? That will also be covered, and then we will touch upon the address mode 3 for today. Okay, so the addressing mode 2 is supported by 9 different formats. So this is basically to calculate the address for the load and store instruction to use. Please remember, different kinds of modes are provided by the processor to compute the address where a memory read or write needs to be performed using these instructions. Now there are 9 ways to do it, but in this particular mode there are 2 things. Now you can either access a word or an unsigned byte. Similarly, store also can either store a word. Always remember, word is a 32-bit value, or it could store an unsigned byte into the memory. So whatever I speak about the different formats, they are all applicable for all these 4 instructions. Okay. One more important thing that we should remember, that there is no S prefix for LDR or SDR instructions. Okay, you remember S is what? If this instruction, can it affect the condition flags of CPSR or not, which is maintained in CPSR or not. If you remember, in a RISC architecture, all the operations within the processor is done only when operands are from a register, correct? So load and store actually helps us in getting the data or putting a data into the memory, which is not, though it is operating one of the registers it is taking, either it will be storing the value or it will be reading from memory and then loading it into the register. So this is something to do with the getting some data into the processor or out of the processor. So there is no data processing involved in this case. So for that reason, the S flag is not affected by this LDR and SDR. So it is only when some operation is done within 2 registers, the S flag is S, that is S means the conditional flags in the CPSR will be affected only when you are doing a data processing instructions, but not during the data transfer instructions. Okay, now this is the format. So if you see LDR or SDR, optionally you can have mention a conditional statement EQ or NE or MI, PL, whatever, and you could say whether it is a byte transfer or not. If you don't mention B, it defaults to a word transfer. and there is no S field. You can see that there is no S within a flower bracket, like what you have seen in the data processing instruction. And then there is a destination register. Whether this value in this register either stored into the memory or from the memory it is copied in. Okay. Now what is this expression? This part of the instruction is what we are going to be discussing in this addressing mode. That is, how are we going to generate the address from which we want to access from the memory. Okay, what is the address at which we want to do this data transfer? The first example is bit complex, but I will explain you so that you understand it, because this you are going to be using it in your simulator. Okay, so if you want to try out different things with the simulator, you should be aware of how to do it, using these instructions. You might have not seen this equal to sign earlier. This is something to do with the assembler. So the implementation of this instruction is also partly left to the assembler also. It can generate multiple instructions to achieve this job. If you remember, I was mentioning if long 32-bit constant needs to be brought into the register, the assembler could use different instructions. It could use MVN or move, or it could put a particular constant in the memory and then try to move that using a LDR instruction. So there are different ways it could be done. So I am explaining you one of the ways where instead of having it in a fixed location, the assembler is trying to get the value using the PC value, using the PC as a reference. Okay, what is it trying to do? In this assembly code, okay, always whenever I put it in the box, this shows the assembly code, what is there in a .s file. I am not showing the full file. We are interested in only this part of this instructions. Assume we have put a LDR R3 comma equal to num1. Num1 is what? Is a variable which you have declared. Where is it declared? It is declared in a data segment that is represented by a .dat. Okay, let me take a pen in case if it helps you. So .dat is a segment, a separate data segment. It is something different with the code where you have declared a variable called num1, and you are saying .word. Please see that there is a dot before. Okay, it may not be visible from long distance. So .word to say that it is a of 32-bit byte and the initialized value is this. Now what does the processor, or sorry, what does the assembler do? It actually allocates a space somewhere in the memory and then it loads it with this value. When you are loading this particular program into the simulator, there is a simulator is having some part of the memory is code, reserved for code. My handwriting is very bad, sorry about it. So and then some data, it has to keep some space for data. Again you have to remember that I am writing like a child, don't worry. Okay, so this memory, who decides where the code has to reside, where data has to reside? The loader, which is taking the compiled binary output of this or assembled output of this file and then loading into the memory. Okay, it is actually maintained by the simulator, some part of the memory. So in a typical our simulator or ARM simulator that we are having assumes the code is starting from address 1000 hex. Okay, it could be modified, but this is what it assumes. So now the code will be here. Now after the code you have put a dot data and then num1. So the simulator is free to use any area to start from and then locate this variable num1. Okay, it is something to do with the internal organization of the simulator and what the loader is doing before loading the program into the memory for it to run. Now assume that it has loaded in some location and you don't know the address. So internally in your program you want to use that address for operating on it. So the instruction provided is for that purpose is LDR R3 equal to num1. So effectively the address in which the num1 is located is loaded into R3. Now there are different ways of doing it. I will explain you one way it could be done, that is with respect to the PC. See, suppose if this data is kept within the address range of 32 megabytes and code is here, okay, and then maybe after some gap data is kept. Now it is easy for the instruction to access the data with respect to the PC. The advantage is what? PC is already a 32-bit value which is available inside the processor. Okay, PC is 6, R15. So it has got a 32-bit value. So if you maybe add some offset to the PC, either subtract it or add it, then you can relatively locate where the data is with respect to the PC address. So what is the advantage we get? We don't have to have all the 32-bit value to be given to the instruction. You can only give, say, take the current PC value and then either you do plus or minus this 12-bit offset, okay, which could be a maximum of this much. Why I am saying F, there is a maximum value. I am writing 3 Fs, each F is going to take 4 bits. So 12 bits is reserved for the immediate offset instruction. So I can mention this much of value into the instruction itself using just a 12 bits of instruction to generate any address which is within the range of PC, current PC value. Okay. So that is why it is used this way, and assembler anyway it will know, the locator will know that if it has to generate this, the data should lie within the range. Otherwise, while assembling itself, you may get a error that this is not possible to allocate, write this way of loading this address. Okay, maybe it may use some other way. It may copy this value into one location, exact address where it is stored, and then it will access using a memory read. So it will read suppose if it is you have a very big program which is going into few megabytes, then what it will do, it will reserve one space where it will store the 32-bit value. Okay, where the address, okay, it will store the 32-bit value which is a 32-bit value which is an address where the num1 is located, and then it will say that okay, you compute the memory this address and then load it from there. So you get a 32-bit value loaded into R3. So this is another way of accessing a 32-bit into the register. So this is the way it is done. Let me first remove all this. Okay, now so this is the way num is data. The address where the num1 is stored is loaded into R3. Other way of doing, other address you may be interested in is, I want to jump to the label by loading that value into PC directly. Okay, that is also possible. PC is what, R15. So we could either do a branch, or I could assign a new address that PC has to be moved into. So that can be done by a label followed by a colon. Then what will happen is the address at which this particular instruction followed by the label is there, that is what it actually means. So when you load this into the PC jumps to this. So after executing this instruction, it will just start executing from here. Okay, so this is also can be done using the LDR instruction. This is I am showing you that control flow can be affected by a LDR instruction also. Okay, there are branch instructions which we will be covering in the later sessions, but just by loading a new value into PC directly by using this kind of instruction, you will be able to change the flow of the instruction. Okay, now these are the things which gets modified. R3 is modified here and R15 is modified with the instruction where move is located. I hope this is clear to you. This is PC relative. Okay, it is done using the current PC value and then adding an offset to that. Always you remember, when we are using anything to do with PC, when a particular instruction is executed, the actual PC will be plus 8 because of the pipeline. Okay, the PC would have advanced by 8 bytes. Okay, because of that you have to comprehend that in the instruction. U means the assembler. Okay, now let us go to the next instruction, next example. Here what we are trying to do, I am saying num1 plus 4. I am interested in wherever num1 is stored, or it is it is in this address and this is the value which is stored there. Please see that it is a 32-bit variable, so you are initializing to 1 2 3 4, which is 16 bits. So remaining upper 16 bits will be all zeros. Okay, in the memory, and then in 0 1 C, which is 4 byte ahead of it, assume that I have stored a value like this. Okay, these are the assumptions. How I do? I can initialize one more. I can put a one more variable and then say dot word. Okay, and then say 0x ABCD. So that will take care of initializing the memory with some value. Now, if I need to access this, I could access it using num2 also, or I can just say num1 plus 4. So this is a fixed arithmetic done by whom? It is not done by the processor. It is done by the assembler, and then the resultant value is kept in the as a constant. Please remember, when you see these kind of things, even in C language, if you are having a hash defined and then saying that 1 plus 2 plus 3, who is doing that 1 plus 2 plus 3? It is a preprocessor. It is not done by the program, executable program. It is done prior to that by the tools. So in this case, the assembler does it because it can resolve the value of num1. It knows the value 4 and then it knows that you want to add. So it can always, whatever is, suppose num1 is 1000, then it will add 4 and then 1004 will be given as an offset into the instruction. Now let me show you an example. Now let us see what is this doing. Assume that after LDR instruction, the next instruction is the move and this is the label. Okay, so the label is actually pointing to the instruction which is next to the LDR, which happens to be a move. And then my intent is label wherever it is pointing, I want to say -4. That means what? I am doing -4 means it is this instruction. And then I am saying load the R15 with that address. That means what? This instruction is loading the PC with its own address. It is like a function calling a function itself, recursive function, or suppose you say while one, continuous looping. So here what happens is when R15 is loaded with its own address, the pipeline is flushed and then it will access this instruction fresh from the memory, again it will execute it. On execution, it will again load the PC with its own address. So what happens when you simulate this? Okay, you will not go beyond this. The simulator will come, execute it, single step it. You come here and then you try to single step it. It won't move beyond because you are effectively loading the same address into PC. So that means it will come back again access the same instruction. So it cannot go anywhere other than executing this instruction continuously. So I want you to try this out in the simulator and see yourself what happens. So this will give you a clear idea how these things work. Okay, it is very important to make sure that you try out all these examples that I am giving in the lecture. Okay, so this is all about first mode. It has taken little more time, but once you understand this, I think you will be able to follow the other mode pretty easily. Let us go to the next one. Again, I tell you, this is we are trying to see what all different ways I can generate the offset, that is this portion. Okay, now the offset is generated using this one, this part of the instruction. And what is this Rn? This is the base register. Remember, this is base register means assume your memory is there. Okay, the base register Rn is pointing at the one location here, and with respect to this, either you can go up by plus adding an offset, okay, by plus, or you can subtract some offsets and access some locations which are below it. That is why the Rn is called a base, because you are accessing it based on this address. You are trying to access different locations around it. Now there are different ways we can do that. So to achieve that, we are using this instruction now. Now let us see what are the preconditions here. I am saying R1 is always pointing at this address. Okay, I have already taken care of using a loader instruction. I have taken care of initializing them, and I have also taken care of initializing the memory also with this content. So please, for any example that I am showing going forward, this is the condition, okay, precondition before executing this particular instruction. Now what is it doing? Loader, load register. Which register? I want to load R5 with what? A value from this address calculated by this. Now I can give plus or minus Rn. So which is Rn and which is Rn? R1 is Rn, R6 here is Rn. So I can give plus or minus. So I am free to give a minus also here. But in this case I have given a plus. Okay. So what happens? R6 is, what is it having? It is having 4. So 4 is here, and R1 is already having this value. If I add 4 to that, because I do not mention any minus, then it is implicit that it is a plus. Otherwise I should have mentioned it as a minus. Now because I have not mentioned anything, it takes it as a positive plus. That means I am interested in accessing the location which is 4 bytes ahead or further from where the R1 is pointing at. R1 is currently pointing at plus 18, so I will be accessing what? This address. Now what does it signify when I am mentioning it inside a square bracket? I want the processor to do this addition, okay, or subtraction based on what I have mentioned, and then use that address to access the memory. Okay, I am very clear. If I am mentioning inside a square bracket, please use what is inside, what have I given you, use that arithmetic operation, whatever you are supposed to do that, and use that address to access the memory and copy whatever is there in it into R5. Now how much I need to copy? I have not mentioned a B here, so it is a word. Okay, I need to copy a word, the whole word. So in this case, one C is there, and then this whole word ABCD is copied into R5. That is what I am showing. Please remember, 0x ABCD means it is not a 16-bit value. Please always, whenever I say R15 or in any register, we mean that it is a 32-bit value. So it shows that all 16-bit values move into it. Okay. So in a hexadecimal, you don't have to mention the zeros, right? Whatever zeros here. So I am just showing the the most relevant part of the value. Now what happens to R1 and R6, which is inside, which is used inside? In this case, they are not modified. Both of them are not modified. I will show you some example where it is modified. In this case, both R1 and R6 are intact. It only uses the value and computes the address and then use it for the starting a memory cycle and reading it from the memory and copying that value into R5. I hope this is very clear to you. Very simple, but I am just explaining you more so that any no doubts are there in your mind. So, what does the name signify? Register offset. That means the offset value is inside a register. Okay, that is what it means. What is pre-indexed? What is pre first of all? Pre is doing something before. Okay, so before accessing the memory, I want to do the calculation. That's why it's called pre. Why is it called indexed? Because I am indexing the memory from the base. That's something I am doing and then trying to access it. So if you see in a typical C world, suppose there is an array with 5. What we call this 5 as is an index. Correct? This is an index. Now the array A could be starting from this address. Okay, which could be, again, I am very fond of 1000. Let me write 1000. And then suppose if I am saying this is a type int in a 32-bit processor. Okay, so that means what? Each element of this array occupies 32 bits. Okay, so A of 0 will be where it will be in 1000. A of 1, where will it be? It will be in 1004. You understand? Now suppose a compiler needs to generate assembly code where you are accessing for loop and then A of I you are doing. I is maintained in the I is a variable, local variable which you have used in a for loop, and then you will be accessing I plus plus and then A of I equal to 10 or you may say that J another integer is equal to A of I. You may do any of this, right? How does the assembler generate code for it? A compiler generates a code for it. It will maintain this J variable in one of the registers. It will maintain the index variable I in one of the registers. Okay, and then it will be using this to access the array. So it can use this instruction by keeping a 4 here. Okay, because it has to advance it by 4 bytes. Okay, and then whenever you say I of 1, that 1 will be into 4. Okay, so it will put that value so that it can use this instruction to access any element of the array. So that is why these kind of instructions are provided. Okay, it is to enable the compiler to generate optimum code. Okay, to access the memory. So R1 can be loaded with the base address of A, where the array A is starting, this 1000, and then it will keep on modifying the index register to access any of the elements here. Okay, so that is a very easy way of doing it. That is the reason these instructions are supported by the processor. And you might have seen in 8086 there are multiple addressing modes, and similar to that, here also multiple addressing modes are supported by ARM. It is given here. Now what is this write back? Okay, what does it mean? See, whenever I am accessing the memory, I am asking the processor to compute it a new address based on the value in R6, but I am saying that please don't modify the original content of R1 and R6 while you do this. That is what I am saying. No write back. So you every time you compute the address and then use it. Okay. Next, if I have another instruction called LDR R5 R1 R6, it will access the same location, or you can say R6 you can put increment by add R6 with the 4, then it will jump one by one. Okay. So a jump means it will access one address after another address, but it won't modify the values in R1 R6 in this instruction. Okay, that's why I am saying R1 R6 no change. I hope this is clear to you. Let us now go to the next mode. Here, if you notice, one new word has come, a scaled register offset pre-index and non write back. So the whole thing is same except that it is a scaled. What does it mean? Let us directly jump. I will not explain about this anymore. You are very clear. See here. Earlier instruction we saw only some register mentioned and then a square bracket came immediately. Correct? Now what is happening? We have added one more. So if you again remember, base register is Rn and the offset register is Rm. So what happens? The Rm, you can make out right. This is the ALU. I am shifting. I am showing it as like this. So Rn is coming from the register file. Rm is coming through a barrel shifter. So now I can give some command to this. Hey, barrel shifter, why don't you do this job on whatever Rm you are reading from the register file and then give it to ALU for generating the address. This is the address that I am interested in the processor accessing it. Okay, this is what ALU. Is it clear to you? So what is the operation need to be done? Logical shift right. Logical shift right is you have 32 bit shift right. Logical shift right, you will be adding a 0 here and then 3 bits by 3 bits. So it will be shifted by 3 bits and whatever goes out will be thrown because it is not going to affect the carry flag because there is no possibility here because there is no S here. So during the address calculation the conditional flags are not affected, so it goes off. Now what happens? You generate a whatever is R6 you are going to be shifting it by 3 bits. Now what is in R6 now? It is actually 1 0 0, okay, or these are all zeros. If you shift by 3 bits, what happens? This 1 goes out of the register, right? So it R6, the shifted value, the whole thing becomes 0 and then whether you are adding, here you see plus or minus is there. So I have not put minus here, so it is a plus. So 0 is added to R1. R1 is already pointing at this location. So effectively you are not doing anything here, which because it is as good as mentioning it as R1. But for an example, I have given you this, okay, and it will be executed the way it is intended because assembler or a compiler cannot optimize this code because it does not know what is the value of R6 when it is executing it. Okay, so there is no, don't think that okay some optimization will remove this instruction and put only R1, and then moreover you are not wasting any time also here. Okay, the same number of cycles will be taken by this instruction irrespective of whether you mention any LSR or not, it will be same. So what effectively happens is it is actually accessing from the same location. I hope this is clear to you. Again here the values of R1 and R6 are not changed, okay, after all these operations. Understood? That's why it's called no write back. You are not writing the newly computed address into the R1. You are not writing it. The address you are just computing it and using it and then throwing that value. Okay. Later on you will again compute it. Got it? Okay. Another type of instruction. Here it is an immediate pre-index and no write back. So what does it mean? Instead of a register, an immediate constant is given. Now what is that width of this? 12 bits. Okay. And then you see here, you please remember minus is here after the hash. So this minus is used by the instruction while encoding this instruction. Okay. But the constant what is stored in the instruction is just a 0x04. Okay. It is not, please don't think that it will be 2's complement of this will be found and that will be stored as an instruction into the instruction. No, it is incrementing or decrementing operation is performed by the instruction inside the processor. So this plus or minus will be considered and then inside one of the bits will be set or reset. I explained you in the last class. So what happens? Is this 0x4 is stored as a immediate constant. So effectively, what is happening here? It is taking the value stored in R2, subtracting a 4 from there. So what happens? It is now R2, that address is becoming a 18 and then that is being accessed and it is loading. So it is loading the value into the register. So R4 becomes 1234 0001234. Got it? This is the way it is done. So why is it called pre-index? Because we are doing the arithmetic before accessing the memory. And why is no write back? Because we are not writing back the R2, we are not disturbing R2. And then why is it called immediate? Because we are using an immediate constant. That's it. Okay. Very good. Now let us go to another instruction. You may wonder why there are so many types of instructions. Because it is the flexibility given to the compiler to use any of them based on the need. Okay. So complex data structures of your high level programs, as I told you how array is accessed, you could have an array of structures. So if you want to access them, then also there are instructions to support it. Now take an example here. It is a register pre-indexed with write back. So that is the difference. You might have noticed this earlier, but this is I am introducing for the first time. So you saw this R2, R6 earlier, but now I am showing you there is an exclamation mark. Okay, this is a part of the instruction. Okay. Now what is happening is it is doing the same pre-index. That means calculating the address because it is within the square bracket. So it is calculating the address to use it in the memory cycle. But now it is the processor is told whatever you compute, write it into R2 now. Okay. So R2 will be modified with what value? Because you are adding 4 to the existing R2 value. Sorry, you are subtracting 4 from existing R2 value. So it will become 18. So R2 becomes 18 after this particular operation. So it will access the same value from the memory. There is no change from what you saw. Only thing is the newly computed address, whatever was used for accessing the memory, is now copied into R2. So what is the advantage? Suppose if you are using this instruction in the same instruction again. Suppose if I had put the same instruction in LDR R5 R2 minus R6 if I do exclamation mark, it will not access the same location. Okay. Now it has accessed this. After this, it will access this. So it will keep on going forward. If based on it is minus I am doing. I am still forgetting about I am doing a minus. So in this case, it will go down. So it will access some location which is below. If suppose if I had put a plus here, then it will keep on accessing towards increasing address from the base. Okay. So the base is kept on either incremented or decremented, and the new value is stored in the base. So base is modified. So earlier I showed that base is stationary and then offset is added. Now base is also moving every time when it is accessing by a fixed amount. Okay. So it keeps on either moving up or down based on whether you have put plus or minus in the instruction. So that is why it's called write back. So the new value, new address what you have computed is written into the base register. Okay, got it. So let us move to other one. Now we are seeing an examples of some write back. It is a pre-index. So this I have already explained you. It will do this shifting operation or whatever, and then the new computed value is stored into register. Now if you want, you can just see R1 is having a 1. So it is logical shift left by 2 bits. So 1 will become what? 0 0 1. If it is you are shifting it by 2 bits, it will become to the left. Okay. it will become 100. That means it is 4. So 4 is subtracted from R2. Again, it is now brought to this address. So you are getting 1, 2, 3, 4 in R5, and then R2 is now changed to 1. Okay, got it. So this is the way the accessing of this is done. I am just showing you different things. Please remember there is a exclamation mark. That is why it is modifying the address of the base register. Very good. Shall we move? So far I have not mentioned something very different. Let me tell you. Now we have seen only the pre-index so far, right? What is post-index? Let us take an example first, and then I will explain you about this. So here, see, this R2 is just sitting there. This is the immediate constant. I want to subtract, but I have moved this out of the square bracket. So what does it mean? I want the processor to use the current value in R2 to access the memory, and then subtract F4 from that address and load it into R2. Okay, that is why it's called post index. It is done after the access is done. Okay, see the difference. If it was inside, then it would have done the computation and used that for accessing. Now because it has gone out, it is given outside of square bracket. It uses this just an R2, whatever is there in R2 is used for accessing the memory, and then it is changed. Now what exactly happens? R2 is already pointing here, right? So it copies that ABCD into R5, correct? And then it changes, because you are subtracting 4 from it, it changes R2 to this. Now you may wonder, there is no exclamation mark here. Why? It is also a optimization in terms of instruction format done by ARM. It is very innovative. See, as a assembly programmer or as a compiler, I have put something here. Okay, doing some -04 or shift left, some operation I am doing. I won't be doing this if I am not interested in changing this register, right? If I am not interested in changing it, I could have just mentioned LDR R5, R2, no need of mentioning anything, or I could have just say is 0x0. So I have an option to say, if I am not interested in writing back, I have an option to either throw this out, not completely don't mention it, or mention it with a 0, then it is as good as saying not to change this value. That is why the processor internally doesn't say in the post index format, it doesn't say it has to write back. It always write back in post index format. That means there is no need for you to mention the exclamation mark. Please remember that. If you do so, it will give a error. So I hope you understood this, because if you are interested in doing something, you are interested in doing this arithmetic operation on the address after the access only to save that. Otherwise what will happen? Suppose you do some value, some pressing or plus or minus or some shift, and then you do some plus minus. But if you don't write into R2, what is the use of doing this whole thing? Because anyway it is not used for accessing the memory, because accessing the memory you are using the same old value. Then what is the need of mentioning this? So if you are mentioning it, that means it is implied that you are interested in changing the value. That is why the ARM designers have using it internally for some other purpose. That if you are doing this, I will always in post index I will do modify the R2. Okay, so there is no separate symbol for this, and I don't treat differently for a post index. Always I will update the register, base register, if it is a post index. Now post index, how will it know? It will know that if the constant or a shift operation is outside the square bracket. So it is very easy for it to encode the instruction accordingly. I hope this is clear to you. So you also see the value what is being copied. R2 is already pointing here, so ABCD is moved into R5, and then it is subtracted. 18 is subtracted, no, 4 is subtracted, so it will come here. Okay, R2 is changed. Without exclamation mark, R2 is the base register is modified. Please remember that. Okay, and the offset is 12 bit because immediate constant. So it is always a write back in a post index format. Very good. Now we are coming to the end of this different modes. You see register post index and always write back. So you can as well mention a register also, and you can mention plus or minus. Now what happens? R6 is 4, so you access as is whatever the value it is R2 is pointing. ABCD is moved into R5, and then you subtract 4 from it. So make it 18. That's all. Very simple. Now by now you should be very familiar that if I give any instruction, you should be able to understand what is happening. Please try out different things in the lab session, and all the modes you should try out and see how it functions in the simulator, so that you will have a better idea. So what do you do? Like what I did, initialize this with the num1 and the LDR instructions that I showed you in the beginning. Use them to load these values with the proper addresses, and initialize this memory with these values with a dot word and then 1 2 3 4. You can write, I am writing 1 2 3 4 to just every byte is different, no, every nibble is different. That's why I have chosen this value so that I can show you some examples. So put this kind of values and then try to access them from the memory into the register, then store some value into the memory. So whole lot of things you can do using these instructions and different addressing modes. So be familiar with this. You may wonder, I may decide to not to use any of this mode, I will use only one mode. So why should I understand these instructions? Please don't take that stand. You can decide not to use some instruction which you are not comfortable when you are writing assembly programming, but if you are seeing an assembled output of a compiler, you don't have any choice. Compiler decides what instruction to use based on which is optimal, which is efficient, which is suitable for the particular code that you have written, and you are debugging it and there is a crash and you are looking at the memory and trying to look at all the instructions which are being executed, and there is when some instruction is executed there is a abort. Now you have to understand the instruction flow which is generated by the compiler. You don't have a choice. You can leave some instructions which I am not very comfortable, I don't like this instruction, so I will not learn about this instruction. You may decide and you may not use that instruction in your assembly code, fine, but you can't take that stand when you are looking at the assembly output of the compiler. So if you want to be a good programmer and a good embedded programmer, understand every instruction of a processor, because you don't have a choice in which instruction is being used by the compiler. And when you are looking at the code which is generated by the compiler, you better understand all the formats of the instructions. So please pay attention to every mode and try out every mode in your lab session so that you are comfortable with all the instructions. Okay, I hope you understand the need for it. I am not trying to sell all the instructions here. Okay, good guys. Now you can sigh a relief. We are going to come to the last. The session is not over, but this addressing mode is coming to an end. This is the last mode, because you see the 9. I told initially 9 modes are there, so I have not missed anything in between. If you are keeping track of the number, see here, whatever you saw inside a square bracket, now I am putting it outside, and then I am not saying anything here. So what does it mean? Whether I mention it or not, the processor is supposed to first use this value what is in R1 to access the memory, and then compute this offset and then do add or subtract based on what is mentioned into R1 and overwrite R1. Okay, always write back. Sorry. Now you see that here is this also I have given. I'm sorry, I have given all LDR examples, but in the later sessions I am having a SDR example. So you can try doing that with anything. It's not that you are to do only all this format with LDR. LDR is simpler because I'm not modifying the memory. It's easy to show you with the same example precondition. But I encourage you to use STR also with all the modes so that you understand the implications of them. You can do all of this mode using STR also. Okay. Now let us understand what happens here. By now you should be able to clearly see that. See, arithmetic shift left. What is arithmetic shift left? Left is what? This one, right? Which register? R7. What is R7 is having now? It is having 1. So 001 shifted by 2 bits. It becomes 100. And then am I doing plus or minus R7? I am doing plus. Okay, for a change I am doing a plus here because I have taken R1 here. So R1 is pointing here. I am doing a plus 4 here to R1. So R1 will start pointing at this location. That's what is happening here. Got it? And but it would have accessed this value because it is a post index. It will use the value what is inside, what was there inside, and then it modifies it with by performing this offset addition or subtraction based on your instruction. I hope now all addressing modes are clear to you. Okay, enjoy the lab session with all of them. Okay, now let me tell you some how it is implemented inside with some example, some more data. If you remember, there was a W bit maintained inside the instruction format to say whether it is incremented or decremented, and then with the optional write back. Okay, if it is 1, you modify the base, return back into the base used for pre-index. Okay, the old value base value is not disturbed if it is 0. Okay, so if it is 1, the changed base address is written back into the base. That means you have mentioned this. Okay, and it is used. This is used for only pre-index. If you remember, in post-index you don't use it, but anyway it is default assumed to be write back. So in the post-index, just for your remembrance, I am saying what is post-index. So the calculation of offset is outside the square bracket. That means post-index. So default this is anyway written into it because if it is a post-index, since it is going to be written always the value, the W bit is not used for a post-index instruction. Okay, in a post-index instruction, W bit's purpose is different. That is nothing of concern to you. Just I am telling you that this is the way the processor is implemented. So write back bit is redundant for in a post index because there is a separate bit is maintained whether it is a pre-index or post-index in the instruction format. So you don't need 2 bits to say to do the same thing because in post-index we have already said that in a post-index this offset what is computed has to be written back into our base register. So we don't want to say the processor they don't want to use the same function in a write by saying that write bit is also 1. So they want to use it for some other useful purpose. So they made this write back bit is 0 in case if it is always they make it 0 in the post index format, but they will write back. The processor will write it back into the base register. Please remember that. Okay. And if you don't want to actually write back anything, please make this whole thing as 0 or don't even mention it. Then it won't be disturbed. The base register will not be disturbed. Now you may wonder why is ARM designer why they have they decided to do this, because they want to use this write bit for some other purpose in the post index data format in a privileged mode. Okay. So what I mean by that is maybe I will give you a slight explanation here later on when we are talking about MMU. We will talk about it. See, processor is here, CPU. Okay, CPU means the whole chip, and inside that our ARM 7 PDMA is sitting. it is accessing a memory using a MMU. It could be inside also. Okay, SOC MMU can be inside. MMU is what? Memory management unit. Now, when it is in privileged mode, it is in operating system is running, and you know that if you have a basic OS understanding, then OS memory space is different from the user memory space. What I mean by that, the MMU makes sure that user don't address the OS memory space, because they can come and corrupt the OS data structure or code by writing some erroneous code in the user space, or maybe by mistake they do, or by intention. Okay, malicious software can try to modify the OS code. So MMU makes sure that if you are in user mode, you are not allowed to access the OS space. That means what? MMU always make sure that in the system mode, when the OS is running, it will always map to the memory addresses generated by the processor to the OS memory space. Now, there are occasions where, see, the OS, okay, the OS needs to access the user space. Why? Suppose if a paging is involved, and then some data, one page of the user space is outside the, it is not got it. Demand paging is then it is in the hard disk and it has to be moved into the user space. It needs to be copied into the user's memory space. So when it has to be done, it has to say, I am not interested in accessing my own space, but I am interested in accessing the user space. So to indicate that, they have used this W bit internally by the processor. So processor is aware which mode the processor is running. If it is in a system mode, it knows that okay, OS code is running now. So if the W bit is set, then it can be used for informing the MMU to access the user space for copying some code from disk to user space or something. So for this kind of operation, this is done. We may spend some time on this later when we talk about MMU. So I didn't want continue to be lost, so I am explaining you here. Okay. I hope you got this. Now I am going to talk about the addressing mode to access the unsigned byte. Okay. We wrote so much about examples we saw with LDR. So I want to show you using one of those modes to access the byte. Okay. So if you remember, if LDR is just a word access, LDRB is a byte access. Now assume this is the way a memory is organized. I am interested in showing you byte level, so I have put it this way, and then please remember whether you are using this whether it is written this way or not depends on the endianness of the processor. Assume the processor what I am having right now executing is in little endian mode. Okay, the simulator also what you will be using in the lab session always maintains it in little endian mode. So what does it mean? Suppose you are interested in storing this value in starting from this address, the least significant byte will be stored here, and then the next byte 56 will be stored in the next address, so on. So 18 is having a 78, 19 has 56, the next address has 34, so it is going in this order starting from the least. That's why little endian. Now you know why I have mentioned different nibbles with a different values, so that you can understand how it is organized in the memory. This is the way it is organized. Okay. Now if you are interested in accessing a byte, you have to say which byte also. So in this case, R2 is actually pointing to this address, and then you are saying +1. That means in this. So you are interested in a byte access. So only one byte stored here is accessed and moved into the register. Now please remember, register is a 32-bit value. So if it is writing EF, you should also make sure that other bits in the registers are all made 0. You may wonder why is it required. I am only interested in copying a byte, loading a byte from the memory. Assume if R5 before this instruction was executed was having some some value, a random value, like this. Only if the load LDRB modifies only one LSB, what happens to the remaining bytes in the register? Because later on this R5 is going to be R5 or whatever the register you are used will be accessed as a 32-bit whole 32-bit will be accessed. So you are going to likely to get into problem if you don't make sure what happens to the upper byte. So if you intentionally you want to only copy one byte, you may have to juggle it out with two registers being used and then R it with the other values and all that. But otherwise, this instruction takes care of making sure that the higher nibbles are made 0. And similarly, this R2 is not modified because there is no this sign. There is nothing like this, so it doesn't modify. So I hope you understand what is the byte access. Now, if you recall, I mentioned that when byte access is done, if it is a store, it will the same byte value will be put across all the 32-bit data bus. All the bytes will be written with the same byte value, so that memory can use it in a way it wants. Here in a loader, so only one byte comes from the memory and then gets into R5 here. Very good. Now let us see one more example. Here I am interested in third byte from base, which is base R2. So R2 is still pointing here only. So please remember, these instructions are all independent. They don't all of them assume the precondition is this. There is no effect of this instruction on this instruction. So it always assumes the precondition is this. That is the way I have shown all of them, so that you understand the different instruction usages. So here +3 means R2 is originally here. So 1 will be bring here, 2 will bring here, 3 will be brought here. So you are interested in accessing AB stored here. So that was what coming here R5, and then the higher nibbles are made 0. Got it? And R2 is not modified because you have not mentioned the not you, I have not mentioned the exclamation mark. So we are done with that. Let us see a few more examples where I am storing a value. Store byte R6 into R1. When we say byte, always the LSB of R6. Oh, I'm sorry, here I'm showing the wrong direction. It should be this way. Sorry. Yes. Sorry. I'll erase it. No, I don't want to confuse you now. See, here storing means this way only. We are doing the value in R6, which happens to be a 4 here. The LSB is 0804. LS byte. Please remember, a byte is 8-bit quantity, so that will be a 04. Now R6 is loaded into R1. R1 is pointing here, so that is why you see that only this byte is changed. Got it? Store is always this way, from register to this. You are storing the register content. Store register. Store the register a byte value only. So you are doing this. One more example. Suppose R1 you are adding it with 01, because initially R1 was our condition is R1 is pointing at 18. So I am adding it with 1 and then using it here. So R1 is made point here. That's why you see that only this byte is overwritten with a 4, because R6 is having a 4. If suppose R6 was having a value 14, you would have got 14 getting written here. So the adjacent bytes are not disturbed. please remember only the particular byte gets written into. Though I say that data memory, all 4 8-bit values will be sent with that 4 whatever is. This is only used by the memory to extract one of the values and then write into the relevant byte. So it will not write in all the places. So only that location will get modified. I want you to try out this so that you understand what is happening with the byte access. Okay, got it? So I have given examples for load byte as well as store byte. So now let us see what are the special conditions you need to remember with the R15, because R15 is always our special register, right? So the ARM architecture, they say do not, okay, they say must not be specified. The write back must not be specified if R15 is specified as a base register. Base register is Rn. In case if you have a Rn as R15, please don't mention this. That's what they are saying. But our simulator allows this, but it will result into undefined instructions, or it could result in the erroneous execution. So they advise that don't do it. I'm not sure whether simulator is allowing, but please refrain from using R15 as a Rn. Okay, there is no need for you. Okay, that is what is suggested by the processor designer. One more thing we should remember, that when using R15 as a base register, even if you are using a base register without a write back, you may use it. Okay, without a write back, you can use a base register. You have to remember that the value what you will be getting is not the address of this instruction, but +8. That is because of the pipeline. I have explained you multiple times. The pipeline, because of prefetch R15 would have advanced to +8. So the operand is read only in the execution stage of the instruction. It is not read ahead. So because of that, what you will be getting R15 as a R15 value is not the current PC value, but when I say the current PC value means the PC value of this instruction, but +8. So you have to comprehend this when you are writing assembly code, or the compiler also will be aware of this and they will generate the code accordingly. Okay, this we should be aware. And then one more restriction is there, that R15 must not be specified as a register offset also. So RM is here, so do not mention R15, and do not, when you say RM cannot be mentioned as R15, you cannot do any LSL or any operation on this also. Okay, because it might lead into a erroneous execution. So that's all, these are the restrictions with the R15. So every instruction will have some special restrictions for R15. So I thought you should be aware of it. This is all what is mentioned in the ARM manual. Okay, be aware. And then about store, there is one more thing you should remember. Okay, if you recall the data path for the load and str in the last session, what I mentioned, I told you that there is one more cycle taken for writing back the value into R1, right? Whether it is write back is there, the same value will be written back, or the new offset value, if the write back is a new offset value will be written back. So one more cycle is taken. So why R15 in the when R15 is a source register of the register store instruction, the stored value, okay, the stored value will be address of the instruction +12. Why? Because if you recall, the address generated by the data path inside the processor is always, it generates the address for the next cycle. Okay, so let me explain you. If you recall, we had shown a pipeline. STR was here. If you remember, add was there, one after the other. Okay, so I told that when STR is there, it is storing a value from the register to the data and the memory. So what happens is, it will be doing on a internal cycle and then moving that value out through the data bus. Okay, Now during that time, the prefetch for this register is already started because that address is generated and then it was put in the address bus. Because while the storing is happening, okay, the previous the next address fetch is already starting. So because of that, the R15 would have been modified to access the instruction after add. That means what? This is +4, this was +8. Now when you are storing the R50, when you are accessing it from the register file, the R15 is already pointing at +12. That is why you are seeing this +12 here. I hope this is you are able to follow. It is only a special condition where R15 is used because none of the registers contents would have been modified because of any of the pipelining operation. But R15 is a unique thing because it gets incremented automatically. So if you use that value to be saved into some memory address, you are going to access this R15 only in the late part of the game. You generate the address for the memory and then you start prefetching the next instruction, and then during that time you are going to trying to save this value. Address generation is started and then you are saving this value. That time what happens, because you are already generating the address, the R15 would have been incremented already by 4, so you will get a 12 instead of 4 in this case. Okay, it's a very unique case. Some of the simulators may not simulate it fully, so it depends on the implementation of the simulator. But please remember, this is the way internally the processor functions, so that you should be clear. So that's why I have given examples for each of the cases. Okay, mentioning about the different write back, different ways R15 could be used. Okay, good. So this is the very complex part of that. Whenever you use R15 in your code, you better be aware that you are going to cause some side effects. So be aware what you are doing. But I still encourage you to change this, try it out and see what happens, because as I told you, when you encounter this instruction, you should be in a position to understand what happens. So unless you try out an instruction, you cannot understand it. Okay, so we are coming to the last part of this address mode 2 is a instruction timing. So what is that I am showing here? Okay, if you recall, I have mentioned about these cycles. Internal cycle is something which is like incrementing the offset value and then computing it. Internally, data path is doing something, nothing to do with the memory access. That is called internal cycle. What is sequential cycle? It is a accessing of a PC. It keeps on accessing the starting from address. Next subsequent addresses are accessed from the memory. Instructions are accessed by sequential address. Similarly, some block of memory, when you are doing a multiple load, the data also can be accessed in a sequential address. Okay, so why is it taking one internal cycle? That is because LDR operation, or even especially LDR, SDR I will be coming here. So LDR instruction has to compute some offset. Both LDR and SDR, they compute the offset using one internal cycle. That's why you saw that after offset calculation, the data transfer happens. Offset computation is one cycle, and then data transfer is another cycle, if you remember. So one internal cycle is consumed by offset. Good. Now why is it oneness? If you see, the accessing the execution of a pipeline in a normal case, okay, when normal flow happens, you get one instruction coming out every sequential cycle. Please remember, the pipeline movement, the execution takes one cycle. That is in this also decoding. After that, one cycle is taken for one sequential cycle is consumed by the instruction when it is pending that in the execution stage. So that is why oneness is given. Now why is this 1n is given? Because when you are loading or storing in a memory, you are generating a new address to do that memory cycle. Okay, LDR or whatever, here we are talking about LDR or SDR. So you are using a a new address you are computing every time. It is not sequential from where the previous access was done. So there is a non-sequential access involved with every load or store. Okay, so this is also executed, understandable. So these are the total amount. So you may wonder why is that separately they are giving S and N, because the S sequential cycle and non-sequential cycle, they all exactly how much time it takes depends on the memory being used. Okay, it is not fixed. Suppose if I in my system I have a 16-bit memory, 16-bit data with memory, then everything I may use 2 cycles for doing the access, similar compared to one 32-bit memory. So the processor doesn't know what kind of memory is being used. That is why it is easy to say in terms of this rather than saying exactly in terms of suppose ARM processor is running in 1 megahertz clock. Okay, just an example. Nowadays, no processor is running in this slow speed. Okay, you can't say that. Okay, it will take 3 microsecond or whatever. You can't call absolute number. You can't give because it is tied to the memory with which the processor is integrated with. That is why they are giving it in this format. So you can always deduce from the memory that you are using. You can deduce how much time this instruction is going to consume for execution. Okay, I hope you understand this. Now let us see. Again, the PC is always unique. It always plays a very important role. Here, what are we trying to do? We are loading R file. Okay, we address whatever is there in R1 into it. Effectively, what we are doing, we are trying to move the control flow. Wherever R15 is currently, we are moving to some location. It need not be a particular location. Some location we are moving it to. Now, won't it involve flushing the pipeline? Because pipeline has already been filled with the 2 subsequent instructions. Okay, whichever was there after this LDR. Now they need to be flushed, and a new instruction whichever the R15 is pointing at has to be put into the pipeline. How much of time will be wasted? 2 sequential accesses. This much of time will be wasted. That is why you see here. Got it? Now this, what is this one internal? I might have put some, whether I put here whether offset internal or pre-index or post-index, one cycle anyway is wasted, internal cycle is wasted for computing the offset. So one internal cycle is done. It has to be spent. Now what is 2n? One is, suppose when you are doing a LDR, you are not loading the value in R1, you are loading the value pointed to by R1. See, suppose R1 is pointing at some address 1000, again whatever is the content here is loaded into R15. That means what? This instruction is doing a non-sequential access of a data. Non-sequential access. This is one non-sequential access, and another non-sequential access is to go to the new R15 and access the code. So one non-sequential, one n cycle is for accessing a code, and one n for accessing a data pointed to by R1. Got it? That is why 2n is here. If you don't understand, listen to this particular explanation again. You will realize everything makes sense. Okay, these numbers. It is very important you understand this so that you completely you are clear about what is happening inside the processor. Very good. Done. Now a store is a little different from LDR, only slight difference. You can see that one is same as this is also same, this is also same, but one additional thing. Why? This is due to store. Okay, that will be because of the store operation is involved, the data value has to go out, so that takes care of this particular additional cycle involved in the storing of value, okay, because the data path is consumed by for loading that value to the data set. Okay, so this ends the summary. Now let us see what happens. Just I want to summarize this. Offset from base, either 12-bit unsigned binary or a second register. Offset could be a pre-index or post-index base from the base. Okay. Modified base value may be written back into the base or kept as is. And LDR SDR has a byte offered which is affected by a NDNS of the processor. Okay. So, and then one more thing which I have not talked about so far, sign extension is valid only while loading a byte and not while storing them. I will explain you. Okay, this is will be explained in the next session. But just suppose you are storing a byte value into the memory, you are interested in writing only one byte. Okay. Similarly, if you are signed byte, if you are loading, okay, signed byte, okay, that's what I am going to be explaining in the next lecture, immediately after this section. If you are loading a signed byte into a register, okay, you are occupying that byte which is being copied from the memory occupies only one byte. But if it happens to be a signed byte, I want the processor to extend the sign so that it preserves the value. Okay, any signed value will preserve its value if the signed bit is extended to any amount of bit. Even if it is a 64-bit value, if you extend it all the way around, it will be the same thing. Okay, so that's why when you are loading a value from memory to the register, because we are moving into 32-bit register, you have to make sure that the byte is sign extended into the upper part of the register. Okay, please remember this is one uniqueness of storing. I will explain you anyway in this word. Now addressing mode 3. Okay, this is something to do with the half word and the signed byte. What is the difference? So far, whatever we have seen in LDR or HDR, we saw how to store or load a word, how to store our word and unsigned byte. Okay, remember unsigned byte. Now we may be interested in storing a signed half word or half word, okay, or signed byte. These are the different things that user or the compiler may be interested in doing. So ARM processor supports it, but this is supported by a different mode which is called addressing mode 3. Let us see. So this is the kind of instruction format. You have to say LDR STR conditional flag, and then you are supposed to say any one of them. Whether I am interested in doing a unsigned half word or signed half word or a signed byte. Now what is half word? 16-bit. Okay. Now what are the other combination? Word and byte, unsigned byte. If it is a word, you would have just said LDR or STR. If it is a byte, you would have said LDRB or STRB. So these two formats are taken care of. Only these three things need to be taken care of. So they have introduced another instruction where you can say with the LDR STR followed by these values. Okay, these are all like similar to what you used to do. Yes, for whether to affect the conditional flag or not, you have to mention this. Then accordingly, it will generate the proper instruction. It will encode it in such a way that the intended transfer happens. So I have shown this. It is only possible with a pre-indexed. Okay, this is a pre-index format. You can make out, right? And then the optional write back is there. Okay, and then this is the destination register. So this is the complete format of the instruction. And if you use this format, if you are using the offset to post index format, the same thing is true with the offset going out. Okay, and there is no exclamation mark here because you are always, this instruction will be writing back the value into the offset register. You got it? So if you are using pre-index format, this post index format this, but actually this is remaining the same. Okay, you have to append it with the one of these values. We'll see an example, then it will become clear to you. Only thing what you have to remember is that the offset value is not as big as 12 bits earlier instructions. It is only a 8-bit value, or you could also, and then register offset is also allowed, and then these 2 bits that are internally used for giving the data type. So effectively it means load, sign byte. Okay, so it is split into load and store. Either load this or this or this. Okay, only in loading you will be doing this, but in storing you will be doing a half word. Okay, so when you are storing, half word storing only is done, and then store byte if you are doing, you would have used a str byte instruction. Okay, so you will not be using this instruction for a store byte, because I told you store byte doesn't have a byte unsigned or signed. It is only unsigned when you are storing it into the memory. So str you could have used it. So this instruction, that's why it doesn't support storing other bytes. Only half word is supported because the str instruction doesn't support half word store. It only supports byte, or if you don't mention a byte, it is only a word. So this is what are the different things supported in this particular mode 3 instruction. Now let us see, we have a precondition. I am having this. Now let us choose a pen here for. So what happens here? I am using a load half word. So load is what? This one, right? So what is 0 to? You have to add whatever is R1 plus 8. So when you add 0 2 plus 8, it is this one, right? So 34 comes to the lower side and 12 comes to this. So what happens is, when you are loading a half word, okay, you are loading into a 32-bit value. If you are only loading a 16-bit value, it's always moved into the lower part of the register. In this case it is R15. So this value which is pointed to by this address, this 34 6 here, okay, and 12 6 here, there is a little Indian. So 34 and 12 6 here. So this is the way it is done. Similar to byte, if it a byte was loaded, it comes to the lower part of the byte, and then it was doing a sign extension. It was backfilling it with 0 when you are doing a LDRB. Okay, you saw the example last time. Now LDRH we are seeing here, which actually copies 1234 and then fills the upper portion of the 16-bit to 0. Okay. Now let us see this. What is it doing? R2 is this value, and plus 2. You can write either just a 0. Okay. At that time you don't have to mention a offset. Otherwise you have to say 2, because it is a 2-byte aligned addresses, right? Half word means it has to be 2-byte aligned. So you will mention it as this one. So what happens? This is loaded CDAB, and then please remember here I am using S here. It's a signed half word. So when I say signed half word, if the loaded value with the MSB is set, the 16-bit value MSB is set in A means what? 10. 10 can be represented by 1010. This is 8. This is 2. So this is A. Correct. So the 16-bit value bit 1 is the highest MSB bit is 1. So that is extended here, because the user is saying, the assembler programmer is saying, I am loading a signed value which is stored in this address. Okay. So in this address, so I want the sign to be preserved. So when it is copied, it will be sign extended. Okay, that is the way LDRSH works. LDRSB is the same thing, but it is for B byte. So when you are saying R2 plus 3, 1 is here, plus 1, plus 2 is here, plus 3 is here. R2 is pointing here. So AB is accessed, AB is moved here into R5 and then sign extended. Okay. So check whether all the simulator does this sign extension properly, but this is what is the intended purpose of this instruction. So if you see the difference of between address 2 and 3, address 2 was only supporting word and unsigned byte. Address 3 supports byte, signed byte and half word accesses and plus signed half word accesses. That's what I have given you examples here. Okay. So I hope this is clear to you. If suppose if it was in big endian mode, then the organization of the data in the memory would have been different. Means the 7/8 would be sitting here, and then because it will start keeping the value here. So big endian, how it will be? 1, 2 will be here, 3, 4 will be here, 5, 6 will be here, 7, 8 will be there in a big endian mode. Okay. So because the simulator is a little endian, I have given examples all for little endian mode only. But you should be aware if there is a big endian mode, how the memory will be configured, and then this instruction when you execute, they will pick a different values because it is stored in a different order in the memory. Please remember, big endian and little endian is something to do with the way it is stored in the memory. Very good. So now another set of examples with a store. What are you trying to do? R7, you are trying to store it in R2. R2 is here, okay, and then R7 is having a value 0, 1, and then it is a half word. So that's why 0, 1 is stored like this, overwritten by this value. Why 1 comes here? Because that is LS byte. It is a little endian mode. So the LSB comes and sits in the lowest part of the memory. So please see that it doesn't sign extend or back with 0 or 1 or whatever. It doesn't do, because there is no way it can be done on the memory. First of all, is it possible for the processor to do this? If it does it, it will be wrong. First of all, you are overwriting into some place where the user was not interested. But even if user is interested in doing it, they are supposed to get this value into the memory and then write back. Or they should have written a whole word with all sign extended and written back. But you can't do it inside the memory like this. Okay. So whenever you are doing a store, it doesn't impact the adjacent bytes or words in the memory. Only when you are loading from the memory, the register adjacent bits are to be modified, because later on this program is going to be consuming this value as a 32-bit value. So if you have copied only 1 byte, you have to know what is you should tell the processor what to do with the remaining bits in the register. But that is not the case when you are writing into the memory. User has some data in it, and I am interested in only overwriting a particular part of the memory. So you do only that and leave it. So don't do any sign extensions, and it can't be done also, but it is not done. I hope this is clear to you. Now one more example we'll see. What happens? I want you to tease it and then see what exactly happens, and then see whether what I am showing is correct or not, so that you can validate whether you understood this or not. Okay. Now this instruction, what does it do? It is store str R6 R1. Store the value in R6. How much? As it has to store a byte or a word or a half word or a signed half word or a signed byte. What is it supposed to do? When you don't mention anything, what is it supposed to do? It is supposed to store a word. Okay. So the entire R6, which happens to be 4, is written into wherever R1 is pointing. So it is supposed to write the whole word. You agree? That is what it has done. So 4 is written, and the higher now see the higher words are also bytes are also modified, because your intent was to store a word. It will do only what the instruction is supposed to do. So it has done that. Now tell me what happens with this. Okay. let me clear this so that you can see what is written here. So we are trying to get whatever is R1 is having, okay, and then please remember these two instructions are within the same box. So the each impact is there on the memory what you see, okay. It is not like this code and this code. This code is together, so it is executed one after the other. Now you are storing again you are doing a store, but this time you are storing a half word in the location starting from R1 plus 2. That means this address, correct. Half word is okay. You are doing a signed word or no? It is there is no sign or unsigned, right, in the store. So you are doing a half word with whatever value in R6. What is R6 having? The same R, it is having 4 only. Nobody has changed it. This instruction also did not say change it. This instruction did not change it. Okay, this is independent anyway. This instruction has not changed the R6. So we'll be having 4. So now what happens? That 4 is written here. Now again you see this byte is also changed because your intent was to store a half word. So it has to be a complete 16-bit value. Got it? I think with this we are coming to an end. I hope all these notes are very clear to you. I took little more extra time to make sure that I don't rush through and you understand the complete things what happens here. So please try out all these instructions, try out all the modes and make yourself clear with the examples, okay, with the simulator, and read up some books also so that your understanding becomes clear. Thank you very much for your attention. Wishing you all the very best with assembly programming. Enjoy the course, the sessions which are coming up later. Thank you.